We finally arrive at the ideal gas equation. This equation comes in two flavours, for moles and for molecules, but they are both arrived at from the same initial experiments and laws. The first law to consider is Boyle's law. Boyle's law says that pressure is inversely proportional to volume in an ideal gas. This seems self-evident to anyone who has ever squashed a balloon. If you press down on a balloon in all directions, you'll have increased the pressure on the balloon. This increased pressure on a balloon has decreased the volume of a balloon. In return, the pressure inside the balloon has increased too. The same amount of gas in a smaller space will hit the sides of the container more often and therefore generates a higher pressure if the volume has been decreased. The gas particles will hit the wall more often without having to warm up or move faster. You can use this relationship in a different way in a hydraulic system. Instead of stating that pressure and volume are inversely related, you can instead say that the combination of pressure and volume will produce a constant figure. If you have a volume of a gas in one chamber connected to a different volume of gas in another chamber, then you can multiply or divide the force exerted in the first chamber into the second chamber, as the pressure times volume in the first chamber is equal to the pressure times volume in the second chamber. If both chambers have the same volume, and you increase the pressure in one chamber, you can also increase the pressure in the other. If the second chamber has a smaller volume than the first chamber, then the second chamber must have a greater pressure than the first. You can play around with the dimensions of the chamber to multiply the force exerted and make a very efficient braking system. In a similar way to Boyle's law, it can be shown through Charles' law that the volume of an ideal gas is directly proportional to the temperature of that gas. From what we know of an ideal gas, this seems obvious. If we increase the temperature of a gas and keep the pressure the same, then the volume of the gas must increase. The converse is true when we cool a gas. If instead of allowing the container to get bigger, we keep the volume of the ideal gas fixed, then as you increase the temperature, the pressure increases. This is called the Gay-Lussac law. Temperature is proportional to pressure and vice versa. Finally, the volume of a gas is dependent on the amount of gas particles contained within that gas. Avogadro's law says that a certain number of moles of gas will occupy the same volume irrespective of the type of gas involved. All four of these laws tell us some important information about ideal gases. We know from Boyle's law that increasing the pressure decreases the volume. Charles' law tells us that increasing the temperature increases the volume of the gas. Finally, Avogadro's law tells us that increasing the mass or number of particles with an ideal gas increases the volume. These three laws tell us all we know about the volume of a gas. It decreases with pressure and it increases with temperature and mass. In other words, we can say that volume is proportional to temperature times mass divided by pressure. The final thing that we know about an ideal gas is from Gay-Lussac. As we increase pressure, we increase temperature. Now, instead of dividing by pressure, we can instead multiply by pressure. Pressure times volume is proportional to mass times temperature. But this is physics, and we don't leave things as proportionalities. We need a constant to turn this proportionality into an equation. If we leave the number of gas particles as just that, then we can express our constant as Boltzmann's constant K. For a situation where we are interested in small numbers of molecules, pressure times volume is equal to the Boltzmann constant times the number of molecules times temperature. PV equals KNT, where K is the Boltzmann constant and is equal to 1.3 by 10 to the minus 23 joules per Kelvin. However, if we have larger amounts of molecules, we want to use moles rather than individual molecules. Here the equation is PV equals RNT, where pressure times volume equals the molar gas constant times number of moles times temperature. R is the molar gas constant and is the same as the Boltzmann constant times Avogadro's number. Although I have written these equations with the constant, the first term after the equals, it is easier, at least for me, to remember them with the constant second in line, i.e. PV equals nRT or PV equals nKT. To me, it just sounds better.